All right, everyone, we are back. 4.36, talking about canonical link functions. So the basic idea is, in the last few sections, we found in a couple of different places that when the gradient of the error function always has this like very kind of intuitive form, where it's the, kind of the difference between the target and your output, and then times the feature, the relevant feature there. And the question is, well, why does that arise? And it turns out that it arises when the posterior distribution on your class, given your point, given your data, is coming from a particular family, and that you pick the way the parameters are determined by your data in a particular way. And so that's kind of what we're going to talk about here. So we'll see that there's kind of a whole family of these distributions that give the same kind of gradient updates, and that kind of explains why we've seen them so many times. Okay, so let's get into it. So for the linear regression model, oh, and yeah, one other thing I want to say was that when we actually do this, there's actually kind of a really cool trick that happens that I think is just worth sticking around for. So I think definitely, yeah, just it's a short section, but I think something cool happens. So stick around. Okay, for a linear Gaussian regression model with a Gaussian noise distribution, the error function corresponding to the negative log likelihood was whatever it was. And if we take the derivative with respect to the parameter of the contribution of the error function of a data point, this takes the form of an error times the feature vector, where the output is some linear function of the inputs, okay, of the features. So okay, that was fine in isolation, kind of made a lot of sense then. But now it says similarly for the combination of the logistic sigmoid and the cross entropy error function, and for the softmax activation function with the multi-class entropy error function, we again obtain the same simple form. So the question is, like, why is this happening? We now show this is a general result. So a general result of assuming a conditional distribution for the target variable from the exponential family, along with the corresponding choice of activation functions. We got to do these two things, okay? So a conditional distribution from the exponential family, so that's one, along with the corresponding choice of the activation function known as the canonical link function. So those two things you got to do, and then you'll get the same form out. Okay. We again make use of the restricted form of the exponential family, and note that we're applying the assumption of the exponential family distribution to the target variable. So previously we've done it for, I guess, the input vector. So here we're just describing the target. And why? Okay, so before we talk about it, why would this be kind of a natural thing to do? So remember that we can motivate the exponential family as coming from these maximum entropy distributions when you have specific constraints. And so that's kind of quite natural. Let's say you have some labels and you want to model them in a particular way. You might say, look, I want to model them assuming I don't know anything except for the mean, and that will give you kind of one member of the exponential family. And you might say, well, I want to do that, but let's say I know what the mean and the variance are, and you'll get another member of the exponential family. So it's quite natural to think of the exponential family as a reasonable model for your data. So essentially incorporating all the information you have, but nothing else. And what we're going to see here is that what we're going to care about is, so we're going to model things with the exponential family and have a constraint. That we're going to have our outputs, or these output variables, determine the mean of this function. So we're going to have a particular member of the family where you constrain the mean, and the mean is what you're going to control with your data. So your data is going to determine the mean of that exponential family member, and hence your distribution on your labels. And so it's kind of makes sense, right? Exponential family requires constraints on some moments of your data. Well, let's just start with the first moment, the mean, and use that to link the labels to the inputs. So that's kind of what we're going to be doing. Okay, so anyway, so we've got our exponential family here. It's going to be, so I remember the way it always worked was, well, and there's different, there are, I guess, different versions, but there will be some term that has to do just with your output variable. There's some term that has to do with your parameters. That'll be kind of the normalizing function. It's an important function. It kind of gives you everything. And then there'll be the exponential term in there where they'll interact. Okay, so now using the same line of argument that led to the derivation way back when, we see the conditional mean of t, which we denote by y, is given by, and remember this function of the parameters. If you kept taking derivatives, I think it gave you like all the moments of your function. So it's kind of quite useful. It contains lots of information. Among other things, it gives you the expected mean. So the expected mean of the output for a set of parameters is related to this this function in this way. Okay. So, therefore, y and eta must be related, and we're going to call this relationship, eta is going to be some psi of y. Okay, so that was kind of step one. That's just coming from the exponential family, and we're going to, so we just define the mean. Now, following Nelder, we define the generalized linear model to be one for which y is a nonlinear function of a linear combination of the inputs. And so y in general is going to be some function of, linear combination. F is known as the activation function in the ML literature, and the inverse of f is the link function, because I guess if you apply the inverse of f to the output, that would be your link to the inputs. Whatever, just some names, just the key thing is remember, it's not the same function. There's a -1, so link function is going the one way, activation function is going the other way. Okay, so now consider the log likelihood function for this model, which as a function of eta is, so we're going to drop the term, that this h term, because there's no eta in it, and we care about solving for eta. So, it's which is going to be ln of this, okay, and where we're assuming that all observations share a common scale parameter, and so s is independent of n. Now you take the derivative just as you would do, and you end up getting the derivative of this term, and then a couple of terms on the outside, which are the chain rule, right? Which is the derivative of eta relative to the parameters on the nth observation, relative to the outputs, and the derivative of the outputs relative to their inputs. Okay. And now, so this will turn out to, this will kind of just simplify to being t of n minus y of n. But now you've got these two terms hanging out on the outside. So you've already seen, we've got our little error term showing up here. Now we've got a couple of terms showing up where a is so and so, and we've used that y of n is this activation function of a, so that's this bit, together with the result for e of t of n. That was our definition. Let's just that was this one. Okay. We now see there's a considerable simplification if we choose a particular form. So let's highlight this, a particular form for the link function f of -1 given by, so if we choose it in this way, why is this important? Because then f applied to psi of y is y, and therefore the product of, if you apply the chain rule, we get f of psi times psi d psi dy will be 1. And then also because a is, a itself is f of minus y of y, a is psi, so you can just plug that in, and now you've eliminated this term, it actually becomes 1. So in this case, the gradient of the error function reduces to this form that we've seen over and over again, and for the Gaussian s is whatever it is. So that's pretty cool. So what we've done is kind of two things again, right? So we've just said, okay, so first let's model our outputs, our labels as coming from the exponential distribution. So that's kind of a natural thing to do in many settings. And now, okay, so now exponential distributions are about constraints. So what is a constraint? Well, the very first one, the most obvious one, is the mean, right? So let's kind of assign that to a particular, to a variable y. So it'll be, and we're kind of aiming towards having, our parameters determine this mean, which will then determine the distribution. So we kind of steer the mean and try to set it so that the distribution that we get, from our exponential family matches the target distribution. So we do that, and we use the fact of the exponential family to relate, this mean to the parameters. And so, we have this kind of this particular form. And now, we plug all of that in, and we find that, okay, actually, because of this exponential family property, there's, the gradient is actually the gradient of the log likelihood is actually quite well behaved. So it's got this term showing up as a difference, this error term. But there's these, these derivatives out there, and the form of those derivatives kind of motivates the shape of the link functions that we take. So there's a considerable simplification if we choose a particular form for the link function, of how f of minus y given by psi of y. And the reason why that's useful is, of course, because it eliminates that term and our gradient becomes simplified. So I think that's pretty cool. Couple of other things I want to point out. So, okay, so this will just say, well, this is going to equal to wt of x, and psi of y is equal to eta. So what have we done here is that this whole approach, we motivated it by setting this derivative to getting rid of this part, but it's kind of like saying, well, we're going to have the means be linearly related to our inputs. So it's kind of linking the parameter. sorry, not the mean, the parameters of the distribution are going to be linearly related to our inputs. So it's kind of an interesting, you might have kind of come up with that, heuristically yourself, but it's nice to see the way it emerges. So I think that's all I wanted to say about this canonical link function stuff. Yeah, I thought again it was very cool because we kept seeing this coming up over and over again. That the gradient updates look the same, and now you know at least one common setting, one common reason why that might be the case. So hopefully that was useful, kind of a little bit eye-opening, nice trick as well, with the functions interacting and how to make them behave nicely. And yeah, hopefully that was cool. Let me know if you liked it, didn't like it, as always. And I will see you next time when we talk about the very important topic of the Laplace approximation. Okay, talk to you then. Bye.